All right, so what I'd like to share with you today is some of the work that I've been doing over the last few years, probably a couple of decades in truth, on what I call ways of thinking. And what I'm interested in really is the notion of thinking without words, and comparing both Corvids, members of the crow family that include the Eurasian jay, here, which should be on the left-hand side of your screen, and children, and particularly as they develop through typically the ages of 2 to up to 11 years. So they're making the transition from pre-verbal to verbal, and what I think these comparisons can reveal about some aspects of cognition or the ability to think. And I'm going to pick 3 sets of examples. So I'll start with something about social cognition, and then I'll go on to something about mental time travel, as Britta alluded to in her beautiful introduction. Thank you, Britta. And then I'll turn to causal reasoning and try and share with you some of the fascinations and problems that I've had in trying to understand these things in more detail. So I'll start with why I'm talking about social cognition and the jays in general. The picture on the first slide was of the Eurasian jay, Aesop here. The picture on this slide is the California scrub jay, the bush hare. California scrub jays have gone through many names. So if you look back at some of my publications, when I first started working with these birds, they were a subspecies of the Florida scrub jay. Then for conservation reasons, they became the Western scrub jay, and most recently the Californian scrub jay. But it's really the same species, they've just changed their name. And what these birds do for a living is they hide food, but they also steal the caches of other birds. And we prefer to call it pilfering rather than stealing, although for the purposes of my talk, I will sometimes call it, refer to them as thieves, but technically in academic papers, I'd always call it pilfering, because I want to make it clear that we're not making any assumptions about the intent of the birds when they take the caches of other individuals. And it seemed to me that the moment you start using words like steal and thief, you're making assumptions that the birds understand that those caches belong to them and that it's illegal to remove caches that are your own versus ones others have made. And obviously we have no evidence at all whether that, to what extent they might understand self-other distinctions, and certainly we have absolutely zero evidence that they understand the human legal system of what isn't allowed. So that's why I prefer in my academic papers to call it pilfering, but essentially I mean taking food that others have made. And this is a big issue for these birds in the wild, because about 30% of their caches of hidden food are stolen by other individuals. And indeed, they go to great lengths to minimize the chance that caches are removed by other individuals. And here are some examples. So the one I want to focus on, which arose out of observations I made when I lived in the University of California, Davis, started as a professor there. And I noticed when I went on my walks at lunchtime, because I'm a movement junkie, so I like to move or dance. And I noticed that the birds would often come down and steal bits of people's lunches, crisps and chips and bits of sandwich and anything when people were busy chatting and distracted. as well as hiding food that was naturally occurring in the wild, like worms and olives and things like that. But I noticed that very often the birds would come back just a couple of minutes later and move them to new places. And I was rather puzzled by this observation, because I'd been taught as an undergraduate in Oxford that the whole point of caching was to hide the food over long periods of time, and that typically these birds might not recover caches for periods of 3 months or seriously long periods of time. And so I was wondering why the heck they were coming back just a few minutes later, when I'd been led to believe that this was a long-term memory strategy. But I noticed that the times they came to recover these caches just a few minutes later was always when other birds had been present and then had left the scene. And so I wondered if it was some kind of protection tactic, the very fact that they seemed to wait till the others had left and then move them to new places. And so I set up an experiment to test this ability in the lab. So as you can see in this slide, and these little images are plasticine models that my husband, Nathan Emery, made. Many of you know him as an academic scientist in his own right. And the idea was that we had the cacher bird, a scrub jay, that was hiding food in a little ice cube tray with Lego blocks around the side. And I came across the idea of using ice cube trays because they're about the right size for the bill of a scrub jay. Most of the scrub jays only get to be about 100 grams in size in adulthood, so they need something fairly small. And I am rubbish at allocentric space, so trying to do anything that requires me to understand spatial locations is a recipe for disaster. But I thought with an ice cube tray, I could do left and right and have numbers 1 to 7 down the sides, not literally written so that the birds could see any symbols, but in my own head it was left 1 to 7 and right 1 to 7. And I struggle a bit with left and right actually, but I've learned over the years that that's lollipop left and that's right. So I had to do it non-spatially. So I used little ice cube trays and I filled them with play sand and then put Lego Duplo bricks around the edge of the board on which I'd nailed in these ice cube trays so that I could make them visuospatially distinct on every trial. And the idea was to have a condition where the cacher is being watched by another bird through a window of a neighbouring cage, and another condition in which the bird isn't being watched. There is no other bird present and it's caching in private. And I counterbalance the order in which these things happened, which is why you see the arrows going both ways, and it was a 10-minute interval between the two. So they either cache in full view of another bird and then cache in private, or they cache in private and then cache in a different tray in full view of another bird. And then 3 hours later, they have the opportunity to recover any of the caches that they made. How can I be certain of 3 hours later? Well, at the end of each of these caching trials, I removed the trays from the birds' cages, stuck them on a trolley, wheeled them out of view, and then brought them back 3 hours later and put them in the same location in the bird's cage. And I was interested in what would happen when they came to recover their caches in private when no other birds were present. And I referred to these as an observed tray, in this case, the purple coloured tray, by which I mean the tray in which they cached in front of an observer, and the in private tray, in this case, the brown tray, the tray in which they could cache when they weren't being watched by another bird. And what I found was that birds that had had previous experience of pilfering other birds' caches, in other words, experienced thieves, were selective about when they chose to move items to new places. Remember, this is always in private at the time of recovery. And what you see here is that in the observed condition, so in other words, when they'd been watched by another bird, they moved the caches and they moved them all to new places, which by definition, the pilferers, the potential thieves, didn't know about because they weren't there to see them being moved. Whereas if they'd cached them in private, very few items were moved at all. And you can see that that contrasts with naive birds who'd had no previous experience of thievery. And you might say, well, how can you be so confident about the experiences of these birds? What, on what grounds are you calling them experienced thieves, or birds that have had pilfering experience, and naive birds that haven't? Well, I should say at this point that all the birds had been hand raised. I took them from nest just before their eyes opened at about day 12. So I was able to control for the kinds of experiences they had and make sure that they'd had no experience of stealing other birds' caches of pilfering in these contexts. Whereas, of course, if I'd done it in the wild, I wouldn't be able to know who had and hadn't had experiences. And therefore, I'd be worried about what previous reinforcement histories the birds had had. And I suppose that's a topic that will pervade all these experiments, really, is that I'm trying to control as best as I can for kinds of experience. And I'm interested in the extent to which I can understand the role of experience in changing certain aspects of behaviour in both the birds and in children. So that was the first experiment. And on the basis of this experiment, my husband, Nathan Emery, and I concluded that it takes a thief to know a thief. In other words, that it's a case of experience projection. The bird that's caching the food recalls its previous experience of either being a thief, having pilfering experience, or of not having pilfering experience, being naive, and then predicts the observer's potential pilfering behaviour, reasoning by analogy with their own experience. So soon after this, Christoph Teufel joined my lab as a PhD student. He'd worked with Julia beforehand, in fact, and he was also interested in various aspects of social cognition. And we decided to see if we could test something similar in children. And we capitalized on a task that had already been developed by Attance and O'Neill, so Christina Attance and Daniela O'Neill, but we wanted to add a couple of control conditions to it. So the basic tenet of this experiment is that a child interacts with the experimenter, in this case, Christoph Teufel, and their parent. In our case, we used the mothers of these children, and we conducted it in their own houses so that the children were comfortable with the environment, because it seems that sometimes when you ask children to respond to their parents covering their eyes or wearing strange things on their eyes, they get agitated. So we did it all in all the children's own homes, and Mummy either has her eyes open or Mummy has her eyes closed during a critical point in the experiment. So knowing that, I learned fairly early on really that when you work with Corvids, the best reward you can give them is a waxworm. When you work with children, one of the best rewards you can give them is a sticker. And so most of the time with the children's rewards, we use stickers. Stickers don't work so well with the jays because they cache them, and it's Devil's own job to find where they've hidden the stickers in the aviary. So it's waxworms for the jays and stickers for the children. So what happens in this game is that the children are collecting stickers, and they have a sort of like a little jigsaw puzzle thing on which they put various stickers. But at some point in the game, the sticker is hidden. Well, of course it's hidden. I work with caching Corvids, so I've got to have an analogy with the caching there. The sticker is hidden in a cup, and there are a number of different cups, so it's not obvious which cup the sticker will be in. You need to have watched where the sticker was placed. And obviously, if Mummy's eyes were open and the sticker is placed in one of these cups that the child can't reach, the question is whether the child understands what Mummy has and hasn't seen, and therefore does and doesn't know about the location of the sticker. And in the initial experiment, Atance and O'Neill found that when Mummy's eyes were open, when the sticker was being placed in the cup, the children would just point at the cup and go get it. Whereas if Mummy's eyes were closed when the sticker was being hidden in the cup, then once Mummy had opened her eyes again, they would explain to her and actually point, not just go get it, but point at the specific cup and where that was located, so that Mummy would know which cup to give the child. Is that clear so far? Okay. So what we did was to introduce two new conditions. So in addition to have seeing, where Mummy can see, and non-seeing, where Mummy's eyes are covered by her hands so she can't see, Christoph and I were worried that children would have had lots of other experiences of non-seeing, such as peekaboo games, and that therefore it would be a good idea to have some artificial conditions about seeing. So we took these swimming goggles, and we had one lot that you could see through and one lot that you couldn't see through. And from the beginning, the goggles themselves look the same, but as you can see in the picture here, we have funky masks surrounding the goggles to allow you to discriminate between which ones you can see through and not see through. So in this particular picture, it's the ones with a blue mask around them that you can see through, and the ones you can't see through are in a yellow mask. And of course, this was counterbalanced. So in half the trials for half the children, the yellow ones were actually the ones you could see through, and the blue ones were the ones you couldn't see through, so that we could be certain that it wasn't anything just to do with a colour preference. And we have, in our seeing question, they'd be told, look at Mummy. This time, Mummy is going to cover her eyes with her hands. Can Mummy see? Or this time, Mummy's wearing goggles. Can Mummy see? And what we found was that we asked them the question, can Mummy see? So we've got two natural conditions. Mummy's eyes are either open and she can see through her eyes, or they're covered by her hands, so she can't see, or they're wearing the goggles she can see through, transparent, or they're wearing the goggles she can't see through, opaque. And then we see what they do about the cup. Once the sticker's been placed in the cup and Mummy's taken off the goggles or removed her hands, so in all cases she can now see again, where do they bother pointing or not? And in the original experiment, when it's just either open or covered, what Daniela O'Neill and Christina Atance found was that when you ask the question, can Mummy see, by and large, the children conclude if Mummy's eyes are open, she can see. If Mummy's eyes are covered with a hand, she can't. And if Mummy's eyes were open, they wouldn't bother pointing, whereas they were much more likely to point if Mummy's eyes were covered. With our with our natural conditions, we replicated the findings that Atance and O'Neill had discovered. And then in our second condition, the ones with the opaque slides, what we showed, as you can see in this graph is that there was a dissociation between how they answered the seeing question and how they answered the pointing question. So with the seeing question, they correctly inferred that if Mummy was wearing the goggles that they couldn't see through, Mummy couldn't see either. If they were wearing the goggles that they couldn't see through, Mummy couldn't see through either. But in both conditions where they couldn't see, they pointed, suggesting a dissociation between seeing and knowing. So they were able to use their experience of looking through the goggles to infer correctly whether or not Mummy could see. But in the absence of seeing Mummy's eyes, they were unable to make the assumption that whether or not Mummy would know the correct location of the sticker or not, and therefore whether they needed to point to the cup or not. In the second experiment, we did the opposite. So in the first experiment, they'd been given first-hand experience of wearing the goggles and therefore knowing whether or not they could see through the goggles. So then the question was, can Mummy also see through the goggles? And can we infer from whether or not Mummy can see whether or not we need to point? In the second experiment, the children were given no experience of whether they could see through the goggles. But Mummy wore the goggles and Mummy behaved quite differently depending on whether or not she could see. So we had one condition, for this I need my handbag, in which there were keys in Mummy's handbag. And in the condition where Mummy could see, she had no problem. Can you see that all right? Unzipping the bag and taking the keys out. But of course, when Mummy couldn't see, Mummy was fumbling all over the place, struggling to find the zip and struggling to find the keys. Mummy also struggled to know how to stack various boxes on top of one another because Mummy couldn't see. Originally, in the discussions with Jim Russell, who was the other author on this paper, we thought that Mummy would just act it. But I was actually worried about whether there would be too much variation in the acting skills of mothers. Some might be very good and others might be rubbish. So we said, why don't we just make them all wear the glasses and then they'll genuinely be able to see or not be able to see. So in the second experiment, there were all these behavioural cues being given off by Mum about whether or not she could see. But that was the only experience the children had. They could read Mummy's behaviour, but they hadn't had experience of looking through the goggles. And in this experiment, we got the opposite result. So on the basis of Mummy's behaviour, either being able to get her keys easily and stack boxes and do things normally, or seem incompetent or clumsy in some way, they weren't able to infer whether or not Mummy could see. Both cases, they concluded that by and large she wasn't very good at seeing. So they weren't discriminating any behavioural difference. But when it came to pointing, they did. In the condition where Mummy had been wearing the glasses in which she was unable to see, they were much more likely to point than when she was able to see. So in a sense, we concluded that this is a double dissociation. In neither experiment have we shown that seeing leads to knowing, but in both conditions, we've shown that we've got an experiment in which they pass the one, can Mummy see, and they don't pass the pointing. In the second experiment, they don't pass the can Mummy see, but they do pass the pointing. So we were suggesting that children are picking up on some cues, but not necessarily the cues that as adult humans we would think are the most obvious cues about whether or not Mummy can see, presumably because of this failure to understand what seeing means with respect to what that means about knowing, experience, projection, and theory of mind. So that's my first example. And now I want to move on to the idea of mental time travel, by which I mean the ability to remember the past and imagine the future. And specifically, I want to focus on the ability to think about the future. And I want to start by sharing with you a little movie clip of my birds at Manningley, and one of the experiments that we conducted together with my PhD students, Caroline Raby and Dean Alexis, and with my colleague, Tony Dickinson, aimed at asking whether jays can take action at caching with the future in mind. And that's what the actual experimental data looked like. So of course, the idea behind the design of this experiment was during training, the birds didn't have the opportunity to cache food. That's why they were given powdered food, and were therefore neither rewarded nor punished for caching. And then it was a one-off test, a novel test in a different time of day in the evening, where all of a sudden they were given food that could be cached, and they were given a caching tray in either room. And we wanted to know whether they would spontaneously place more food in the hungry room, given that they didn't know which room they would end up in that evening, and therefore whether they would be hungry in the morning or not. And in fact, in subsequent experiments, we had rooms that served different kinds of breakfast, let's say eggs in one room and toast in another. The birds, like us, like variety, and therefore they would cache the equivalent of toast in the room that served eggs, and eggs in the room that served toast. We're trying to do something similar with children. We thought it best to avoid food, especially given food allergies. And instead we had, rather than a breakfast room and a no breakfast room, we had a room that served toys for breakfast and a room that had no toys, a breakfast room. This was done in collaboration with Christina Attance and her student, Christello. And we did two experiments. We asked the children aged 3, 4 and 5 years of age, where would you like to cache these toys or put these toys, those little basket, either for right now or for tomorrow on your next birthday. And obviously, if you're planning ahead, then you should say you want to put them in the no toy room, in Big Bird's room. And what we found is that children of 3 years of age showed no preference for the toy or the no toy room, whereas the children of 4 and 5 years of age, when it was done as for tomorrow, made a very distinct preference to put the toys in the no toy room, in Big Bird's room. Whereas when we asked them about the right now, they, even the 3-year-olds were able to do it. So it wasn't the 3-year-olds couldn't understand the basic task, that it's a good idea to put the toys in the Big Bird room or the no toy room. It's specifically about the future. And we've done other experiments. For example, I did one with Jim Russell and my then PhD student Alexis, where we asked them to play a blow football game, and they had to then decide what they wanted to save for tomorrow. And we saw a similar pattern of results, that these abilities seem to, 3-year-olds fail, 4-year-olds can sometimes do it, and by 5, these children are relatively good at future planning. So I now want to come on to the third part of my talk. So I've talked about social cognition, and I've talked about future planning. I now want to talk about physical cognition. And one of the discoveries we made just over 10 years ago, probably about 12 years ago, is that although it was well known that certain animals such as New Caledonian crows and chimpanzees and capuchin monkeys use tools. We assume that most of the corvids didn't use tools because there was no evidence that they were using them in the wild. And then we discovered that actually first our rooks and then jays, and now it's also well established in ravens, that these corvids will happily use tools if they're given a problem that requires them to use a tool. So that's opened up some ways of us looking at physical cognition in these birds. And this is one task that we've developed, which Nathan Emery and his then student Chris Bird called the Aesop's fable water task. So the idea here is based on the Aesop's fable where there's a thirsty crow and the crow puts rocks into the pitcher to raise the water level. Because it was thirsty, in our case, the birds are not thirsty. This is Romero, a Eurasian jay, but they love these waxworms that you could see floating on the top of the tube, and they will readily add stones or other objects into the tube in order to get the worm, which is done by dropping the stones in the water and raising the water level. That, because it's such a simple test, it's just one tube with water in it, and all you have to do is you can change the substrate, so you can change whether it's water or air or a solid like sand, and you can also change the kinds of objects that they place in to the tube, and we're able to show in a series of experiments that firstly it's a goal-directed action, so if the worm is not on the top inside the tube but somewhere else, they don't bother to put objects in it. If it's filled with air and the waxworm is magically floating on the top thanks to a bit of blue tack, or the object is resting on the top of the solid such as sand, they don't add objects to the water. We then wanted to look at whether it matters what kind of object. So we gave them some novel objects, some that sink and some that float. And here's an example of this. So here we've got marbles that sink and pieces of cork that float. And this was the first trial. You see, even removes the offending item that gets in the way and then takes his prize. And here you can see the results for the two birds that were tested. They both put far more of the items that sink into the tube than items that float. We did the same thing with children, and by now you'll know that we use stickers, not waxworms, as our reward. So here's an example for the children. And the children get the sticker. Now you might think that's a measly little sticker. Why would the children care about that? Well, they can swap that tiny little sticker that floats, because it's hard to find stickers of any size that easily float, to then get a big fancy sticker with the University of Cambridge, I'm as clever as a crow on it, which they all love because they can't get stickers like that anywhere else. So we then gave them the choice of some items that float and some that sink. And this is the performance of a 6-year-old boy. I think you can see I haven't got all the details quite down. This is a 9-year-old girl. This is what the results look like across age. So you can see that 4 and 5-year-olds are at random, 6 and 7-year-olds are not much better, but by 8, they've really got the task. And in fact, 6 and 7-year-olds improve over time, but it's not until 8 that they solve the task. So where do I want to take it from here? Well, I've tried to give you some examples of how I've used some different kinds of tasks, both within social cognition, future planning, and physical cognition or causal reasoning, to look at the performance on certain tasks in the Corvids or the crows and the children. What I now want to talk about is how to put these together. And I suppose at the beginning, I should make it explicit what I'm not saying. I'm not trying to make any claims that because jays pass, for example, the Aesop's fable water test, that shows that jays are as intelligent as 8-year-old children. That is not what I'm saying. There are many differences between 8-year-old children and jays, including wings and hands and education and all the rest of it. What I am trying to do is try to understand some of the roadblocks in thinking and blind spots in seeing, and how those constraints might influence the decision-making processes that animals make, including human animals. So what I wanted to do with the water task, because it's such a simple task, is see if I could explore in any detail why the children were passing that task so late. Because it seems really surprising that children don't pass until they're 8 years of age. I mean, it's not as if they haven't had any experience of items that sink and items that float. I mean, most children have bath times and playthings in their baths, you know, rubber ducks and sponges that float and bits of soap that sink and so on and so forth. So it seemed very surprising. So what we thought we would try and do is tease apart the difference between functionality and reward. So we had 4 conditions. The first one pictured at the bottom in yellow, we can see the cursor here, is in which it's both functional and rewarded. So this is the condition where there's a solid object that sinks, and therefore when you choose the solid object that sinks, the water level rises and you get the reward. So that's basically like the marble condition in the movie clip. And the not functional, not rewarded, the second case, hollow, F minus, R minus, that's like the condition with the little bits of cork that float, because obviously in that case you've put those in, the water level doesn't rise and you don't get the reward, be it a sticker or a waxworm, depending on whether it's a child or a jay. But then we wanted to have 2 other conditions in which either, although it's not functional, it is rewarded. So this is the red condition, float, or it is functional, but it's not rewarded because it leaks. So what we're trying to do here is contrast whether the children's choices are informed by paying attention to whether in previous tasks it's been rewarded, or whether they're paying attention to whether or not it's functional. So let me give you some examples of how that happens. So in the exploration case, they have some tubes, and they're all going to be different from in the actual test phase, in which they simply find that the one that would be functional, in other words, should sink, leads to a reward, or it should be functional because it sinks but doesn't lead to a reward, which is the pale case on the right-hand side of your screen. Or if it's not functional, in other words, it floats, either it's not rewarded, just as with the cork objects, or even though it isn't functional, it is rewarded. There's some other magic mechanism, if you like, going on that means that regardless, it's still rewarded. And then in the experimental phase, where they get two tool choices, they get given two of the objects. So in number one here, that would be the one that isn't functional and isn't rewarded versus the one that is functional and rewarded. So it's obvious what they should do there if they've understood the task. But then there are other ones where you're making interesting comparisons, such as the case of the red and the blue, shown in number 2, where you're juxtapositioning whether or not it's rewarded or functional. So this shows one of these conditions, the surprising conditions where it's either functional but not rewarded, or rewarded but not functional. So in this condition, you can see that as the items go in, even though they're floating, it still works. And here you can see a video.
And 1, 2, 3, go. Did you get the token?
Yeah.
Why?
Because they kept, because you turned it and then it went down, and then the red things moved.
Okay. Why don't you choose a sticker?
I'm not sure she quite understood the details of the experiment. I think if I was interviewing an undergraduate student and they gave me that level of detail, I'd be less than impressed. But she did understand that she was getting the reward. And of course, it was a ratchet twisting mechanism that meant that even though she was only inserting floating items, so non-functional items, because of the ratchet mechanism, the magic mechanism, the water level was rising, and therefore she did get the reward. This is the opposite condition. This is one in which these are functional, they're solid items that sink, but they don't get the reward because the tube leaks. And you can see that pictured here, that as the items go in, you can see that although the water initially rises, it then leaks through the sides, and therefore the child will never get the sticker. And this is what it looked like in the actual training.
I'm going to give you these and this, and you have 1 minute to get the token. Do you think you can get the token?
No.
Why not?
Because there wasn't any more.
There wasn't any more what?
There wasn't any more of the blue thing.
All right.
So again, I'm not sure she got the details right, bless her. And I should say that it was a minute for all the different kinds of experiences that was obviously controlled for. So having had these experiences of tubes that would leak, and ones with a ratchet, and the normal ones where the items sink and the water rises through natural causes or float and doesn't rise through natural causes. They were then given a new tube. And the idea now is they were given a selection of objects. So for example, in this case, they got a selection of ones that either weren't functional and were rewarded. So they floated, but they'd still been rewarded in the past during the previous training, or they were functional. They sunk, but they hadn't been rewarded in the past. And the children were asked to choose 5 of these items. There were 10. And then we analysed their choices. So in this particular case, they'd chosen 2 non-functional ones that had been rewarded versus 3 functional ones that hadn't been rewarded. So here's an example.
You think you can fish it out?
No.
All right, so I'm going to give you this little tray here. And I'm going to give you these 10 objects that you played with before. Do you remember them? Yeah. I want you to choose 5 objects that you want to use to get the token out. The 5 objects you want to use to get the token out, I want you to put them in the little tray over here. Okay? Which 5 would you like to get the token out? Put them in the tray. All right.
So that's an example of the exploration phase. And here's the results that we found. This is the percentage of children in each of the age groups from 4 till 10 plus. 10 plus was 10 to 11-year-olds that chose 95% or more of the expected objects for each strategy. And what you can see is that reward history, so what had happened in the training trials and the exploration phase, didn't guide their choices. But as they started to understand about functionality, all of a sudden their performance increased. We'd like to do something similar. Obviously, next step, of course, is with the Jays, and see whether their choices are also guided by functionality or reward history. Because in a way, that's a way of kind of reformulating the idea of, can it be explained in simple associative processes, in which case reward history should work very well. If it requires an understanding of functionality, that's a reason for suggesting that's something more complex than simply attending to previous reinforcement history. So children don't rely on the experience of being rewarded in the past during the exploration phase to drive their choices. But from the age of 8, these function-based or functionality strategies are significantly better at predicting behaviour than reward-based strategies. So as children get older, functionality increasingly becomes the factor they take into consideration when selecting the tools in the novel test phase. So back to, just to sort of finish off now, I want to look at it from the other point of view. So I've looked at kind of how we can think about what the crows do and how that could explore novel experiments in the children, such as reinforcement history versus functionality. But the other way around is to say, well, what is it about the Corvids? And of course, many have argued, most notably Nick Humphrey and 10 years before him, Alison Jolly, about the importance of the social function of intellect hypothesis, and followed up by many others, such as Robin Dunbar, arguing that really what made the primates unique was the complexities of their social living. And Nathan Emery and I have argued that when it comes to highly social corvids, for example, the rooks, the sarcrea, that they have quite complex social relationships, that they have these long-term alliances, just as chimpanzees do. They have analogous ways of maintaining relationships, so grooming in the chimpanzees, preening in the corvids, food sharing, active support during fights, and kissing, or if you're a corvid, you don't have lips, but you can use your bill to twine and do something similar. And here are some examples. Here are the jays food sharing. Here are the rooks doing some of their social displays and a bit of bill twining. And of course, then there's the challenge of monogamy. And Randy Glassbergen sent us this lovely cartoon of looking at some of the challenges of monogamy in humans. When you've been married a long time, you get to know what the other person thinks. No, you don't, he says. And we see quite complex synchronicity in the birds. These are two of our rooks, Cook and Fry. And for me, as a dancer, this looks a bit like avian tango. There's a leader and there's a follower, but they're pretty synchronous in their movements. So the final thing I wanted to share with you with some experiments we've done using food sharing in a similar vein, I suppose, to the way we've used food caching to look at aspects of cognition in these birds. So in this experiment, we capitalized on the fact that Eurasian jays readily share food with a partner. Many birds show courtship feeding. The advantage in the jays is that they transfer one item at a time. So the male sits at the food sharing window and he's offered two types of food. In this case, the foods are waxworms and mealworms, and he's given a choice. And the male can either share the mealworms with or the waxworms with the female. These were experiments conducted during Yerka Osagic's PhD and in conjunction with two other then students, Rachel Shaw and Lucy Cheek, both of now who have lectureships. And the idea was that what we were going to use was specific satiety as a tool to see whether the male would be selective in which kind of food he shared to the female. So during the specific satiety phase, they're either fed mealworms or waxworms, and then they're simply given a choice of both foods. And the idea is that they should learn rapidly over 2 or 3 trials that having just eaten waxworms, it's mealworms I want. Having just eaten mealworms, it's waxworms I want. And this seems to be a very reliable phenomenon throughout the animal kingdom, including human beings. Work inspired by my colleague Tony Dickinson and Bernard Belaine, showing how rats need to learn that it's food that satiates hunger and water that satiates thirst. So that's just the basic setup to make sure that our specific satiety paradigm is working. And this just shows you that indeed in the difference in proportion eaten, if you've just eaten a lot of waxworms, you're more likely to prefer mealworms. And if you've just eaten lots of mealworms, you're more likely to prefer waxworms. And we have to do it relative to baseline because the jays vary a lot in how much they eat. So Hoy could eat about 85 worms before getting sated, whereas Chinook got full on 4. So you have to do it. That's why we do it relative to maintenance diet. And then in the critical experiment, having been having had the opportunity to learn that if I've eaten lots of waxworms, it's mealworms I'll want, and if I've eaten lots of mealworms, it's waxworms I'll want, the male then gets to see what the female has eaten in the seen condition, or she gets to eat, but his view is obscured, so he can't see her during the unseen condition. So he can either see what she eats or he can't see what she eats. And then in the test phase, he's given the choice of waxworms and mealworms. And the question is, what does he choose to feed her? And the idea is that in the seen condition, if she's just eaten lots of waxworms, you should feed her mealworms. If she's eaten lots of mealworms, you should eat her waxworms. But of course, the issue there is that does it really depend on what he's seen her eat, or is there something else about her behaviour that would give him clues as to what she might want? So a behaviour reading account, irrespective of what he's seen her eat. That's why we have the unseen condition. And you see here that in the seen condition, if he's seen her eat lots of waxworms, he gives her mealworms. If he's seen her eat lots of mealworms, he gives her waxworms. That's not the case in the unseen condition. So if she is giving off cues, the male isn't using those cues to inform his choice of which foods to give her. Now, of course, you could say, well, maybe it's nothing to do with how she's behaving. Maybe it's something to do with his observation, that if he's just seen her eating lots of food, that's kind of the same as if he's just been eating lots of food himself. He's just then bored with that food. So we ran a control condition that we called observational specific satiety, in which he can see what she's eating, but then she's off in the other side of the aviary and he doesn't have the opportunity to feed her. But will the fact that he's seen her eat lots of food affect his own choice of what he himself wants? And the answer is no. It's quite different from the specific satiety case. So if he's eaten a lot of the food himself, he wants the other food. If he's seen her eat a lot of food, that doesn't guide his choice of what he wants to eat. So wrapping all that up, I've tried to show you, using evidence from social cognition, from future planning, and from physical cognition, some of the ways in which we've tried to investigate aspects of both Corvid cognition and the developmental cognition in young humans. And I wish I could claim that all this was novel and all this was the ideas of the very talented, clever members of my lab, for whom I'm very, very grateful for all their hard work. But the Reverend Henry Ward Beecher beat us to it hundreds of years ago, because in the early 1800s, he said, if men had wings and bore black feathers, few of them would be clever enough to be crows. So with that, I will finish, and I'd just like to thank everyone in my lab, the feathered ones, the Corvids, and the unfeathered ones, all the wonderful PhD students and postdocs, and my collaborators and funding. And most importantly of all, thanks to all of you for listening.